Having proved the roll-down lemma, we are now ready to prove the Fourier integral theorem. That is this theorem. Suppose f is integrable in the real line, and f is bounded variable in some small interval around x. Then the conclusion is that fx plus fx minus divided by 2, the mean value of the right and left hand side limit of f at the point x will equal to the d lambda minus infinity positive infinity ft cosine lambda t minus x dt. In particular, if f is continuous, at x, then the left limit and the right limit at x equal the value of f at x. The result becomes the left hand side is fx Okay, so this is the Fourier integral theorem. We obtained intuitively at the very beginning. Okay, that is this integral, this formula at the beginning of this lecture. Okay, so now we prove this result seriously, and of course we can replace the bounded variation property of f by another condition, and even more general condition, but we will not consider that problem here. We simply prove the bounded variational case as a demonstration for the idea. Okay, so the first step to prove this result, we prove this result. That is when alpha goes to positive infinity, the integral from minus infinity to positive infinity fx plus t sine alpha t divided by t pi t dt is the mean value of the two-side limit. We prove this result first. With this result, we will obtain the deserved result of the theorem immediately. Okay, so we know that we studied the integral in the limit. We know that fx plus t sine alpha t by pi t dt. This integral can be divided into 4 parts: minus infinity to minus delta. The delta is the positive number mentioned in the theorem. That is the radius of the interval over x, where f is bounded variation. That is our delta. So plus minus delta 0, plus 0 delta, then plus delta to positive infinity. Now from the lemma, we know that this integral, we know that AB gt sine pt dt goes to 0 as t goes to infinity, right? The condition on G is that G is AB, and AB, the absolute value is finite. That is, G is absolutely integrable over the interval AB, and our result containing the case that B is positive infinity. So applying this result to the first and the last integral of our condition of our this decomposition, because this is our GT. This is our GT to apply the lemma integral lemma, because in the first integral and the last integral, 0 is far bounded away. The interval for integration is bounded away from 0. Therefore, such a GT, that is fx plus t, x is given, and divided by pi t, is integrable, absolutely integrable. So we can apply the lemma to see that minus delta minus plus delta positive goes to 0 as alpha goes to infinity. We have this result. Therefore, we only need to study the two integral in the middle, the second and the third integral. The discussion of the second and the third integral are similar. Therefore, we only study the third integral. Okay. So to study the integral, we know that by the Jordan lemma, we just prove. We see that 0 delta fx plus t sine alpha t divided by t dt goes to fx plus over t over 2. Okay, this is by Jordan lemma. Jordan lemma, let's go back to have a look on Jordan lemma. Jordan lemma is that g is bounded variable and gt sine alpha t over t. This is the integral in Jordan lemma. So in our case, our GT is actually fx plus t. Applying this to Jordan lemma. Jordan lemma says that 0 delta gt sine alpha t dt goes to half of pi, then g 0 plus. You compare the conclusion of the Jordan lemma, which is g taken by fx plus t. You will see that this is true. Similarly, we have a similar result, that is minus delta 0 fx plus t sine alpha t divided by t goes to a pi t here. We have a pi. Goes to f x minus divided by 2. The pi, we move the pi. For Jordan lemma, we move the pi on the right hand side to the denominator of the left hand side. The result is still valid. So we apply this modified version to our situation. So from these two, we know that our I2, this is just our I2. This is I2, and this is I3. All I2 goes to half of fx plus, and I3, that is to say, I2 goes to half of fx plus, and I3 goes to half of fx minus. Then substituting this result to this equality, the first and the fourth term goes to 0. The middle term, 2, and the second and the third term goes to half of fx plus and half of fx minus. Therefore, in conclusion, the integral goes to the mean value of the left and right limit of f at x. So proving our this conclusion. Okay, so at this point we just prove this result, because the integral in this limit decomposed into 4 parts, and the first and the fourth part goes to 0. The middle 2 parts convert to half of the right and the left limit of f at x respectively. Therefore, altogether, the whole integral goes to this number. Okay, so this proves this result. Now, with this result, we can easily prove the conclusion of the Fourier integral theorem. Okay, so our 0 alpha d lambda minus infinity, consider this integral ft cosine lambda t minus x dt. This integral we switch the order of integral, write it by minus positive, then dt 0 alpha ft cosine lambda t minus x d lambda. We switch the order of the integral. Of course, how can we switch the order of an infinite integral? This is a question. Unfortunately, we cannot prove this here because this requires the discussion of integral which is a parameter, which is not the required content of our course. So we have not spent time to establish the related theory for this kind of operation. But we need this result at this point, so we simply apply the result. Our f justified this. The condition on our f justified this multiplication and this operation. Okay, so for this integral, the value of integration is lambda. So this ft can be moved out of the integral. Then the integral of cosine lambda t minus x can be computed easily. So this after that computation, you will obtain the minus infinity, positive infinity, ft, and then we obtain this result alpha t minus x. Then t minus x dx. This is just by a direct computation of this integral 0 alpha cosine lambda t minus x d lambda. Consider t minus x as a constant because the integration variable is lambda. Then the antiderivative of cosine is sine, so it is easy to see that this gives us this result. Okay. Now in this integral we make a change of variable. This integral can be changed by f t plus x. Maybe I write as I let t minus x by s. Then t is x plus s. So x plus s sine alpha s divided by s ds. Okay. So by the result we just prove that is this result, this limit we prove at the very beginning. We see that of course our integrable variable are replaced by s. That is not essential. So the limit is goes to fx plus fx minus then pi, because we do not have a pi here in our this computation, so we need to add a pi here. Okay, but you after divided the pi, move the pi, this limit is valid when alpha goes to positive infinity. When alpha goes to positive infinity, the left hand side is the integral from 0 to infinity. So we obtained that 0 to infinity d lambda minus infinity, positive infinity, f t cosine lambda t minus x d t is half of fx plus fx minus, then pi. And you move the pi to the left-hand side, give us the conclusion of the Fourier integral theorem. And this completes the proof. Okay. For the Fourier integral theorem, we can write this in another interesting form, because cosine lambda t minus x can be written by exponential of I lambda t minus x plus exponential of minus I lambda t minus x divided by 2. So we have fx plus fx minus this by the Fourier integral theorem, that is minus 0 to infinity d lambda minus infinity positive infinity ft cosine lambda t minus x dt. Then replacing the cosine here by the exponential expression given at the top of this page, and then make a change of variable. For the second term, you minus lambda to be a new lambda, okay, to be a new lambda. Then just by some easy computation, you will obtain that this is 2 pi. Because for the minus lambda part, it gives us an integral from minus infinity to 0, which the 0 to positive infinity will obtain the minus infinity to positive infinity d lambda minus infinity positive infinity ft exponential of I lambda t minus x dt. And exponential of I lambda t minus x can be this part. I lambda x part has nothing to do with t. Therefore, this is ei lambda x minus ei lambda t. So we move the ei lambda x to the beginning, out of the inner integral. This gives us 2 pi minus infinity positive infinity e minus I lambda x d lambda, then minus infinity positive infinity ft ei lambda t dt. Okay, we obtained this result. Now, for a given function f, we called this this is minus infinity positive infinity ft ei lambda t dt. This is called the Fourier transform of f, the Fourier transform. Okay, and we also called given a function g, we also called gt exponential minus I lambda, I should write g lambda exponential minus I lambda x d lambda. This is called the inverse Fourier transform of g. Okay, so because of the Fourier integral theorem, we have a Fourier transform and the inverse Fourier transform. Now, when g is continuous, the left hand side is fx. When g is continuous at x, then the left hand side is fx. So this equality, fx equal this integral, just equivalent to say that fx equal the Fourier transform then take inverse transform. Or simply f equal taking Fourier transform first and then taking inverse transform. So under the assumption of our Fourier integral theorem, and if f is continuous, then we have this result everywhere. Okay, but this also justify why we call the G as the Fourier inverse transform of G. Okay, why we call this pair of transform? One is transform, the other is inverse. Okay.